will be telling us about boundary algebras in Qubit.
Okay, great. So thank you very much for inviting me to talk in. So yeah, this is some upcoming paper that should be out soon with Edward Witten about what it says. But let's start with some more basic general question, which is the relationship between Euclidean quantum gravity path integrals and canonical quantization of quantum gravity. Okay, so Euclidean path integrals are great. They let us compute all this stuff. You know, Bekenstein-Hawkey entropy, things like the Hawking-Page transition. These days, page curve, Hayden-Preskel, all that sort of stuff. But they're also obviously very hard to interpret. And yeah, on the other hand, canonical quantization is great because it's actually quantum mechanics. We have states, operators, everything we need to do the usual formalism of quantum mechanics. We can define things. And unfortunately, the relationship between them is somewhat unclear. So in particular, you know, all the brilliant Euclidean calculations of entropies, starting with the calculation of the Bekenstein-Hawkey entropy, tend to involve things that, from a bulk point of view, have no obvious state counting interpretation. So you have, say, some thermal circle in the bulk that is just completely contractible, and you know, what does that even mean? Why are we calling that an entropy at all? Well, we're calling it an entropy because it gives answers that are consistent with Hawking radiation and everything like that, and we like those answers, and so we take it. But it's not obvious how to mix it. So it's even been suggested that the two are sort of unrelated or not necessarily related. Daniel Harlow's made this point very forcefully and eloquently. And there are sort of, you know, particular examples of very simple theories, such as canonically quantized JT gravity, which I'll talk about today, where at least for pure JT gravity, the canonical theory is completely well defined, but it doesn't understand what the Bekenstein-Hawkey entropy is. It doesn't know anything about that. It certainly has no notion of microstates. It has no notion of the right spectrum or anything. So there's a paper by Jaffris that pointed that out very nicely. But in the last year, starting with a paper by Witten and then by me, Edward, and Ben, we can actually derive the Bekenstein-Hawkey entropy as a statistical entropy of a von Neumann algebra, not as just some classical thermodynamic entropy, by considering sort of canonically quantized quantum gravity in the strict semi-classical limit g goes to 0, where it basically becomes QFT plus maybe one or two extra gauge modes. And you know, so that's suggestive that you know, maybe you don't need Euclidean stuff, or you don't need magic and holography to get all these answers. Okay, so what I'm going to talk about today is to try and explain the meaning of the Bekenstein-Hawkey entropy and what it's counting and so on in a full theory of canonically quantized quantum gravity. And in particular, I don't want to be putting in by hand what the answer is supposed to be. I'm not a loop quantum gravity person. I want it to just be forced on me by the theory, okay, but without resorting to Euclidean black magic. And I also want to explain why and how it's related to these Euclidean computations we know and love. So I'm going to do that, in fact, in JT gravity coupled to some bulk matter theory. But first, I'm going to review what happens in sort of pure JT gravity, where, as Harlow and Jaffris claimed, we don't get the Bekenstein-Hawkey entropy out. It doesn't know about it. There's various other problems. Then we're going to add bulk matter to the theory. We're going to still have a completely well-defined theory that we can describe very precisely. And we're going to see that suddenly the Bekenstein-Hawkey entropy, including the sort of Schwarzian corrections and stuff like that, are just going to pop out, and it's going to be imposed on us by the theory, okay, without putting any Euclidean input. So just to get a bit speculative, possibly the general rule, pure JT gravity does not have Hawking radiation, and it doesn't know about the Bekenstein-Hawkey entropy. If we add bulk matter, we actually have Hawking radiation. It has a meaningful temperature, and it also knows about the Bekenstein-Hawkey entropy in a precise way. So you know, speculatively, these two things could always come hand in hand. Okay, I should say the entire talk I will be taking the topological term S0 to infinity. So the bulk topology will be completely fixed. We won't have to worry about wormholes or anything like that. So it's all going to be very basic stuff. We have some things to say about wormholes. I don't have time to say about it. But yeah, and most of this talk is going to be about why certain calculations are the right thing to do and the right way to interpret things. a lot of the actual calculations will have been said in more or less similar words by other people, and I'll try to appropriately cite stuff. A lot of people have written papers on JT gravity. But yeah, the goal is to be really precise about why all these calculations make sense in the context of a canonical quantized theory. I mean, so there will be an infinite S0 term, and there is an ambiguity related to the normalization and subtraction of that term. I will be defining up to that ambiguity, which means that yes, entropy differences will be precisely defined. The absolute values of entropies will be infinite because we took S0. Okay. Okay, so JT gravity is very familiar to everyone, so I'll just be quick. The action's given by this thing. We have a dilaton. We have that has a linear potential. We have a boundary term. Blah blah blah. And then we impose boundary conditions that we have some cutoff, a large value of the dilaton, and I define some boundary time little t that has a proper length rescaled by epsilon relative to bulk. Okay, so we can choose coordinates for ADS2, have sigma and global time t, and sigma's like a radial coordinate. Looks like this. And then finally, the sort of only dynamical objects in pure JT gravity, as most people are familiar with, are the locations of the two boundary particles. Okay, so we're just working the strip. Topology is fixed here. So we have a left boundary and a right boundary, and they're each described by two coordinates, the global time and this coordinate chi, which is like a rescaled version of sigma. Chi r and chi l means how far out towards the boundary they are. I'm taking notation from a paper by Jaffrus and Kolkmeyer here. Okay, so before we worry about any constraints, then pure JT gravity is just described by L2 of r to the 4 wave functions on these four coordinates, TL, chi l, tr, and chi l. Okay, so before I talk about the constraints, I can talk briefly about the boundary charges and the boundary Hamiltonians. So the ADS2 background has an SL2R isometry group. And again, you can look up in Jaffrus and Kolkmeyer the action of that SL2R isometry group and the boundary charges given by these formulas. So these first terms, these terms linear in the momenta, they're just generating the sort of the usual charges of a particle in ADS2. These terms are just to make the whole thing Hermitian. Finally, these terms are the boundary particles feel an effective magnetic field, right? That's what stops them falling into the bulk and instead go out to the boundary. They have the right extrinsic curvature, and that's what leading to these extra terms here. Okay. So we also have boundary Hamiltonians that just generate time translations of these boundary times, little tr and little tl. And these, it turns out, are just they commute with the charges because they're gauging around things, and in fact, they're just the Casimirs of these charges. So they're given by these formulas. So this is all in this nice paper by Jaffrus and Kolkmeyer. And now we need to worry about some constraints to get the real physical JT gravity Hilbert space. So there's actually two separate constraints we need to worry about here. The first is that the two boundary particles need to be space-like separated. Okay, so we need to have the difference between the two boundary times, modulus, be less than pi. So you can't send a signal from one boundary to another. That's just physically there's no configuration. Yeah, it's like we could, in principle, if we just looked at the dilaton gravity, there's also points where phi becomes really big, sort of 2 pi into the future, because of the way a Rice-Nordstrom solution works. But we don't think of those as physical boundaries. We think of the physical boundaries as the two space-like separated. Okay, and of course the second constraint is the more familiar one to most people, which is that the SL2R symmetry is a gauge symmetry, so it should be treated as a gauge constraint. Okay, so we should be removing redundancy of degrees of freedom to get rid of that SL2R. I should say, by the way, that the first constraint on its own would not make sense to impose if we weren't also imposing this gauge constraint. That's because boundary time evolution in general will take you from states that are space-like separated to states where the boundaries are not space-like separated. It's really this gauge constraint that makes it consistent to impose this and still have a well-defined Hamiltonian. Okay, so now we want to impose the gauge constraints, and it turns out that's slightly subtle because SL2R is a non-compact group, and as a result, there are no normalizable gauge invariant states. That's just a fact about the theory. So what people often do is they do a non-rigorous approach as physicists, where we just say SL2R is an infinite volume, we're going to divide by that, and then claim the state is normalizable. But there's a better way to do it, a more precise way to do it, to use what's called the Hilbert space of covariance, or the group averaging procedure. So I want to explain that because it's going to be important later when we have matter. Yeah. You could, I think what you're, sorry, it is, the Hilbert space will end up being L2 of R. I think the way you're thinking about getting there is to impose the gauge constraints at the classical level and then quantize the theory. I'm wanting to impose it at the quantum level. I want to go to the unconstrained quantum theory and then impose the gauge constraints on the quantum theory. Yes, yes, yes. The physical Hilbert space is normalizable. I'm saying that in the unconstrained Hilbert space, there are no normalizable gauge invariant states. That's not how we're going to define the physical Hilbert space. Okay, so let me give a simpler example of a theory that has the same problem. So suppose we have a Hilbert space on L2 of R2, so two coordinates x and y, and we have a gauge symmetry that's translations in the x direction. Okay, we want to quotient out by that gauge symmetry. Spiritually, that should leave us with just wave functions on y, right? So as physicists, we'd like to say that the physical wave functions are just like functions on y that are constant in the x direction. But of course, these are not normalizable states, so they're not actually in the unconstrained Hilbert space. And in fact, if we try to impose, look for states to be invariant under translations, then there aren't any, because they can't be normalizable in the x direction. So instead, the right way to do it is to say that any wave function psi, not necessarily invariant under the gauge constraints, is a physical state. But then we impose an equivalence relation where we say two states are actually the same if they're related by gauge transformation. So some psi of xy and psi of x plus ay are equivalent states in this theory. Okay? So with the usual inner product, that would not be a legit thing to do because those states would have different inner products. But we can define a modified inner product called the physical inner product, which is defined by taking the sort of naive inner product and integrating over elements of the gauge group in between. Okay, so this is actually can be normalizable for normalizable states phi and psi. And manifestly, we get the same inner product for psi and for g of psi, just because the hard measure is invariant. And so this is a well-defined thing on the quotiented Hilbert space, and that gives the Hilbert space. Okay. No. So after we impose this equivalence relation, it really will just be this Hilbert space here, in fact. We'll work through it more explicitly for the SL2R case, and we'll see you sort of get the right number of degrees of freedom. But basically, the point is, you can have a lot of wave functions, psi of x, y, but most of them are related by translations to each other, and so this quotient like kills off most of those extra degrees of freedom. So this does give you what you want. Yep. Yes. In general, because if I translate phi as normalizable wave function, I translate it by some very large amount, then the inner product between them will get very small. And so that makes the integral converge, even though it's non-convergent. Yeah, that's the point of this procedure. Okay. What I should say, the nice thing is the operators on this covariant Hilbert space are just the usual gauge invariant operators on the unconstrained Hilbert space. So for states, we have to do this weird procedure. For operators, then everything is. Okay. So let's do this for SL2R. Okay, so we're starting with wave functions with just this constraint that the difference between TL and TR is less than pi, and we want to quotient out by SL2R transformations. Okay, so we do exactly the procedure I described above of considering arbitrary states, but treating them equivalent if related by gauge transformation. Turns out we can always use, given this condition, we can always find some SL2R transformation that will take TL and TR to 0 and set chi-L and chi-R equal to each other. Okay, so we're sort of shifting the two boundaries. We have three degrees of freedom in SL2R. We shift the two boundary times to 0, and then we equalize the positions of two boundary operators. So it's sufficient within this physical Hilbert space to restrict ourselves to wave functions of the form a delta function at TL equals 0, delta function TR equals 0, and the two chi's set equal to each other. Okay, I've dropped the R here just because there's only one chi left now because I set them equal to 0. But chi is chi R. Okay, so we can just only think about states of that form and we'll still get all physical states by doing so. Yes, so as you see, in the unconstrained Hilbert space, these wave functions are not normalizable, they're very bad. But they are normalizable in the space of covariance. You can just do this group averaging procedure on this thing, and you'll find that in fact, the norm of this state with that physical inner product is just the norm of chi, where we integrate, integral of chi, d chi of chi phi star phi. Okay, so it is normalizable states with respect to the physical inner product that we care about. Okay, so what we conclude is that the final Hilbert space we end up with is just wave functions of this one degree of freedom chi, so it's just L2 of R. So this is, Daniel said, it's just scattering wave functions. It's just L2 of R. And there's some natural operators that act on this thing that preserve this form of the wave function, which is just chi, and I called it p chi. It's the sum of p chi R and p chi L. Okay, that preserves the form of this delta function. So those are operators that preserve this sort of gauge choice. And so they're natural operators on our constrained Hilbert space. Okay, so we now want to find what the physical Hamiltonians are in terms of this degree of freedom chi. So the way we do that is to note that because we have this integral over G in the physical inner product, then the sort of SL2R charges, which are the sum of the action on the left boundary particle and the right boundary particle, should annihilate all physical states. Okay, so on any physical state psi, which you can take to have this form, then the action of J1 is given by the sum of momentum operator on the left and right. J2 is given by a difference. J3 is difference between two chi's. Okay, those can be replaced by 0 without changing anything in physical inner products. Okay, so remember we had these forms for the right Hamiltonian and the left Hamiltonian that were not equal to each other, that involved these PTRs, PTLs, and so on. We can substitute in, replace, say, a PTR by a minus PTL or by a plus PTL. So we can actually just delete those terms using these things because these annihilate. Do a load of work on that. And what you end up finding is that the two boundary Hamiltonians can both be rewritten as just p chi squared over 8 plus a half e to the 2 chi. Okay, so this is exactly the Hamiltonian you saw in Henry's talk or something like that. We were just a little bit more careful in how we derived it, but it's basically the usual story of getting. Okay, so this has a purely continuous positive spectrum, just consists of scattering states. And we can now ask the question, sort of, what are there natural algebras associated with the two boundaries? Okay, so remember I said the gauge invariant algebras are just, operators on the unconstrained Hilbert space that commute with the gauge constraints. So they're just operators acting on the left or right boundary particle that commute with the gauge constraints. The only such bounded operators, in fact, just bounded functions of the left or right boundary Hamiltonians. So these boundary algebras are actually completely commutative algebras. They're purely classical. And they're also, in fact, equal because we just showed that HL is equal to HR. So the same algebra on the left and the right. And finally, because the Hamiltonians have a non-degenerate spectrum, they're in fact each other's commutants. So the left boundary operators are the set of all operators that commute with all the right boundary operators and vice versa. The same operators in this case, but they are each other's commutants. So that's an important property that we'll see again show up later. Okay, so this is a bit weird because in holography, we want each boundary to be sort of described by independent degrees of freedom. And so there shouldn't be any shared operators between the two boundaries. But in this case, we found that all the operators on either boundaries are shared. So this is sometimes called the factorization problem. The spelling here is not just because I'm British. I'm following convention proposed by Henry Maxfield, that this should be the factorization problem with the S, and the factorization problem with the Z should be the maybe more familiar one involving partition functions, because Z is for partition functions. So I think everyone should religiously stick to that from now on. I want to advertise it here. But yeah, this is sometimes called Harlow's factorization problem. I don't know. It was certainly emphasized in some very nice papers by Daniel. Sorry, no. Okay. So we're almost done with pure JT. But let's just comment briefly on how we would define entropy on this thing. So there's a natural states on each boundary are just a probability distribution for the energy. So there's a natural definition of entropy, just the integral over h of this probability distribution times its log. Okay, so you can define that as an entropy. It's called the continuous Shannon entropy, the differential entropy. But there's two problems with it. First, it has absolutely nothing to do with the Beckerson-Hawkey entropy, which is completely different. And the second, if we replace h by some function of h prime, then we get a different answer for the entropy. So there's an ambiguity in what the entropy is, and it's a very big ambiguity. Yeah, that's also a problem. Yeah. But if we chose the right h prime, we can in fact match the Euclidean answer. So you could add that as some extra input as the right way to calculate entropies, but the theory is not telling you it. The canonical quantized theory doesn't know that that's the right thing to do. Okay, and there's a reason for this, which is that P defines a linear functional on the Hilbert space, but that's not what you need to define an entropy. What you need is a density matrix. You need an operator. Okay, and to map linear functionals to density matrices, you need a trace. So what is a trace in this context? It's just some positive linear functional that satisfies the property that trace of AB equals trace of BA for all operators in your algebra. But in this case, the algebra is commutative, so any positive linear functional will satisfy that property. It's like totally boring. It's totally arbitrary what we choose as our trace, what we call our trace. If we add that in as extra input to our theory, then we can match the Beckerson-Hawkey entropy. But we don't know that in advance. It's not natural data. So there's the Jeffries-Kohlmeier paper. They talk about adding in defect operators. In this language, what they're doing is adding in the right trace to match the Euclidean answers. But they're having to put in extra data to the theory by hand. It's not there in the plain JT theory. Okay, so now let's go on to JT gravity with matter. We'll hopefully be able to do it fast because we don't do exactly the same things. So I'm just going to couple the pure JT gravity theory to an arbitrary bulk quantum field theory. I'm not going to assume it's conformal. I'm not going to assume it's free, anything like that. It's just some QFT Hilbert space in ADS2. Okay, so before enclosing the constraints, the matter is now we have the two positions of the left boundary, two positions of the right boundary, and we have this matter Hilbert space that just is what it is. Okay, the constraints are the same as before, except we have this extra term that's the action of the SL2R on the matter Hilbert space. Okay, so to impose the constraints, we again go to the co-invariant Hilbert space, and we do essentially the same thing as before, except so we can again use the SL2R gauge transformations to write our wave function as a delta function TL, TR, and chi-R minus chi-L. The only difference is, that now this wave function psi of chi is valued in the matter Hilbert space. So it's a map from the real numbers to the matter Hilbert space H matter. Okay, so we've added in that matter Hilbert space. The physical Hilbert space is L2 of R, this chi tensored with H matter. Okay, so that was all basically the same. But now let's think about what happens to the physical Hamiltonians. So we do the same thing as before. We're going to use the fact that these J1, J2, and J3 annihilate all physical states. But now they're defined differently. So now we have this extra term that they also include the action of the matter charges. Okay, we do the same substitutions, but this time we end up with two formulas for the left and right Hamiltonians that I believe not been obtained before. They're probably related to some Henry showed yesterday that was specific to a single particle in the bulk. These are completely general, any bulk matter state. They're just the different formulas for each other. P chi has been replaced by P chi plus or minus J3 charge, translation charge of the matter, and then we also have these sort of null matter generators times e to the chi, the extra thing. We started from the same Hamiltonian in the unconstrained thing, but then we went to the physical Hilbert space. We did some substitutions using these things. These things now include matter charges, and so we get matter charges showing up here. And so that's why we now have matter charges in there, and these two formulas are no longer the same. Okay, You stick these things all to 0, then you get the same formulas as before. Okay? We've gauge fixed. We've gauge fixed to a gauge whether boundary particles at TL and TR equals 0, and yeah, so they are gauge invariant because of the gauge fixed. Okay, so the two Hamiltonians are now different. We can have matter that makes the two energies different, but they do still commute. Some non-trivial calculation, you can do it. And they're also still positive. In fact, they still have the same continuous positive spectrum as before. I should say that in the normalization we've done, these two operators are actually negative semi-definite. So this term is positive semi-definite. So slightly, turns out to be the natural conventions for the charges, but it may look slightly weird. These are like, yeah, this minus these things are like a null Hamiltonian, you know, like the null translation operator. Sorry, say that again. The algorithm J matter is SL2. Yeah, you have to use that. That's very important, making everything commute and so on, but it all works out if you use that. It's a non-trivial calculation that can be done. Okay, so now let's think about the boundary algebras. So it's no longer the case the only thing we can measure at the boundary is the Hamiltonian, because we can also measure matter fields at the boundary, okay? So in Edward's talk and in our paper on semi-classical black holes, then the boundary was sort of in a well-defined location. And so matter operators near the boundary generated a sort of type 3 matter algebra associated some causal wedge of that boundary. In this case, JT gravity, the causal wedge fluctuates depending on the state of the boundary particle. So there's no single well-defined causal wedge. There's no single region of the bulk that we can reconstruct, or that is generated by boundary matter fields. In fact, you can show that the global time of the matter, the boundary particle at t equals plus infinity doesn't commute with its time at minus infinity. There's not even some basis of states with well-defined causal wedges. No state has a well-defined causal wedge in JT gravity except at sort of very high temperature. However, we can still define local matter operators at the location of the boundary particle. So given some primary field phi with dimension delta, just define a boundary matter operator as just the bulk matter operator where the boundary particle is. And because it's near the boundary, it actually, the chi dependence just looks like e to the delta chi. So it's very simple dependence on chi. You can check that this is gauge invariant roughly because chi of r and t of r transform in the opposite way to phi does under the SL2s. So these define local operators. Local operators are not very well defined, but if you smear them out over a little bit of boundary time, that's like smearing them out over a little bit of bulk time, that should give us some bounded operators. So that lets us define a boundary algebra generated by the boundary Hamiltonian together with these primary fields of the boundary. Okay, and similarly, we have a left algebra. So clearly, conjugation by boundary time generates time evolution of these fields, vector TR. And we claim that these two algebras are A, each other's commutants again, and a B are in fact type 2 infinity von Neumann factors. Okay, so let me sort of unpack each of those claims. So an algebra is a factor if there's no non-trivial operators that commute with everything else in the boundary, in the algebra. Roughly this is true in this case because the Hamiltonian doesn't commute with matter operators and matter operators don't commute with the Hamiltonian. So there's nothing that commutes with everything. If we smear in time in quantum field theory just in time, that's enough to give, in Lorentzian time or Euclidean time, that's enough to give a bounded operator. For like well-defined states in the continuum Hilbert space, then it's a well-defined operator. Oh, I may have not meant to say bounded. I may have meant densely defined rather than bounded. Sorry, that may be my bad. Yeah, good point. But we can bounded functions of them will be bounded and well-defined. Okay. Okay. So the second claim, this with type 2 infinity von Neumann factor. What does that mean? Well, it means there's no microstates, no single boundary states. That means it's not type 1. Hopefully you remember von Neumann algebras from Edward's talk. And the fact that it's type 2 is just because we're going to find a trace on it. And I'm going to define a trace on the next slide. So that's why that's true. The final claim is that the two algebras are each other's commutants. So this is somewhat less obvious, actually. It's sort of manifestly true that the two algebras commute. You can check that very easily. You might also wonder whether there's some other operators that commute with both of them. And in particular, with JT gravity with matter, we can have arbitrarily long wormhole states, where sort of there's stuff in the middle that can't be seen from either side. So it's very non-obvious that this is true. I'm going to give an argument for it in a little while that will be involved going to a Euclidean picture. Hopefully I have time. Okay. Okay, so what is the trace? Well, yeah, so if it is indeed a type 2 infinity factor, then it has a unique trace. So if we can find one trace, then that is the only thing we could have chosen, and it was forced on us from the theory. We didn't choose it. So let's just try and find something that gives the right answer. And we can actually use Euclidean path integrals to do that. So Euclidean path integrals let us define a sort of Hartle-Hawking state prepared by some Euclidean evolution of time beta. Okay, and by construction, that satisfies something that looks like kind of like the property of the trace. Phi1, phi2 is equal to, sorry, that should be a 2 and that should be a 1. Apologies for the typo. It equals to the same two things commuted past each other, except this t gets replaced by t plus I beta. Okay, this is the so-called KMS condition. Okay, so that is not a trace, but what we can do is we can just define the trace as the limit when it exists of the expectation value in the state beta as beta goes to 0. As beta goes to 0, this beta goes to 0, and we get the property we want that the two operators commute. So that is a trace, and because we've argued it's a factor, then it's the only trace. So it really is being forced on us from theory. I should say that in the limit beta goes to infinity, this Hartle-Hawking state actually becomes a delta function at chi equals plus infinity. So in Henry's talk, he talked about calculating things by starting with length equals minus infinity. That's the same as chi equals plus infinity. So that's really what he was doing there. I'm just attaching some slightly more precise, I would say, words to that same story. Okay, so once we have a trace, we can define entropies. One finds, for example, that the trace reduced density matrix of a Hartle-Hawking state is just e to the minus beta h. And then we plug it in and we get that its entropy is just the Euclidean formula. Okay, so everything matches, at least for thermal states, with the Euclidean answer. And I really want to emphasize, because it's the whole point of the talk, that this result is entirely forced on us by the algebraic structure of the theory. We did not put in any input from the Euclidean theory. We used it to show that some properties were satisfied. We could have done that without it if we really wanted to put in the effort, but it's just there manifestly. It just follows from the canonical quantized theory. There's a well-defined Hartle-Hawking state that is normalized and that satisfies the KMS condition. I have no S. I'm dropping the S naught. These are renormalized entropies here, right? It's a type 2 algebra. There is an infinite thing being subtracted. If I do the Euclidean calculation without an infinite S naught, then I just get something finite, and that's the type 2 entropy, which has an infinite constant subtracted. Edward? Yeah, I think that's separate from what Daniel was saying, but it is worth saying that if I have, say, the identity, then the limit as I take beta goes to infinity will be infinity. Okay, that's because it's a type 2 infinity algebra. But if I have something like e to the minus beta h for finite beta, then the limit of that as beta goes to, as the other beta goes to infinity will be finite, and so it has a well-defined finite trace. Yep. Yes, so this is coming out from the fact that we're forced to find some trace that is cyclic, and we're getting that out of it just from the algebraic proof. Sorry? No, I don't know the relationship with what people try to say about that. I expect there is one, but I haven't really tried. It could be that you can see a relationship, but yeah. Okay, so I want to very briefly explain how this is in general related to Euclidean construction. So let me just do that. So the idea is you start from just an algebra built out of formal strings of symbols that are like e to the minus beta h's and like matter operators and so on. Okay, and we're just going to use that abstractly to define an algebra where multiplication just means take two strings of these things and concatenate them together into one longer string. Okay, so that's abstractly an algebra. And then we can define a trace on this algebra by mapping strings to a Euclidean path integral on the disk, where we close up the string and then evaluate the path integral on the disk. That manifestly satisfies the trace AB equals trace BA. We can also define adjoints by just reversing the order of the string. So together, those things give us enough structure to define an inner product between two strings as the trace of string dagger string. Okay? This inner product is positive semi-definite, has a load of null vectors, but we can quotient by these null vectors to get a well-defined Hilbert space, just abstractly defined from these strings. Okay? This is, by the way, essentially equivalent to Marov-Maxfield construction, but I won't say any more details about that. And this thing is acted on naturally by sort of itself from either the left or the right. That gives us two algebras acting on it. Basically, by construction, those two algebras are each other's commutations. So how does this relate to everything we said before about a bulk theory defined in a completely bulk way? Well, there's a natural map from this formal Euclidean Hilbert space, the bulk Hilbert space, just by taking a Euclidean path integral on a half disk. So starting on the Euclidean boundary and ending on a geodesic, that defines a map from one to the other. That map manifestly preserves inner products, so it's isometric. And we claim that in fact it's an isomorphism. Okay, so any state in our bulk Hilbert space can be prepared by Euclidean path integral. In fact, you can do it with Euclidean path integrals with only one matter insertion, superpositions of them. Basically, the idea is that by acting with a local operator on the Euclidean boundary, we can make any matter state we want. And then by evolving in Euclidean boundary time, we can make any chi be anything we want as well. And so we can get a dense set of states in this way. Okay, so this is the final slide I'm going to say. Had a couple afterwards, but I can skip them. So why do Euclidean entropy computations work? Well, it's easy to check that in this abstract string picture, by construction, with the trace that we defined, then the reduced density matrix of the string S is just S dagger. Okay? But this is exactly the usual gluing rules that we use to compute Euclidean entropies using the replica trick and so on. Okay? S dagger means glue the two strings together, i.e. glue the two path integrals together at the opposite boundary, and that gives us a density matrix. Okay? But we've successfully shown that there's a one-to-one map between those computations and the computations we really care about of algebraic entropies on a canonically quantized Hilbert space. Okay? So yeah, there's a story about super JT with matter, but I'll just flick through it. There was a really interesting paper by Juan and Henry and a couple of other people where you have states that have zero energy on both sides, even though they have non-BPS matter in the middle. Using these sort of technologies, you can like exactly count those states and really look at how many there are, see them very explicitly in a Hilbert space picture. Okay, but I am over time, so let me just say that what's the takeaway from all this? So as Harlow and Jaffa has said very correctly, canonically quantized pure JT gravity has a factorization problem and it doesn't know what the Bekenstein-Hawking entropy is. On the other hand, it also doesn't have Hawking radiation. So let's stick some Hawking radiation in by adding matter. Then the two algebras stop being simple commuting algebras, they become factors. So, depending on what you mean by factorization problem, that is now gone. They're type 2 factors, but they're factors, so they factorize. But the trace is unique, and it gives entropies that agree with the Euclidean answer, including things like Schwarzian corrections, up to this renormalized divergent term. So one could say that within its domain of validity, then all the problems of pure JT gravity get fixed by adding matter. So can extend the formulation to super JT, as I briefly mentioned. Can also include perturbative wormhole corrections. I didn't talk about that, but there's an interesting story there. Doesn't work quite as well because JT gravity with matter with wormholes isn't very well defined. But yeah, that's there's stuff to say. But yeah, I think that the broad lesson is that canonically quantized JT gravity with matter is a very nice, well-defined theory that has all the properties we should expect of it. It has infinite entanglement entropy, but it has factors on each side, and it has the right entropies come straight out of canonical quantized theory. Okay, that is what I have to say.
Have you thought about the case where you look at one-sided black holes and you put it under the roll branch?
No, I haven't thought about that. Yeah, you could. I would guess that the story goes through quite similarly, like that it's equally well defined, at least without wormholes and so on. But we haven't thought about it. Henry?
You still have a factorization problem in the sense that there's no representation of these algebras on Hilbert spaces that are tensor H, right?
Yeah, so exactly. So that's why I said it depends what you mean by factorization problem. You might say you want the Hilbert space factorized into a tensor product. We don't have that, but we know the reason for that, right? It's that we needed to kill topology changing processes, and so we had to take S0 to infinity. And so the right thing to expect is a type 2 infinity factor where S0 has given us that. So it's giving us everything we should reasonably expect of it as a theory. Yeah.
So two questions, I guess. One is that I would normally have said that the Euclidean path integral gives even the S0 term.
Yeah. So yeah. So it knows about shifts in S0. If, as Daniel said, if you make S0 infinite, then it gives something infinite. But if I make S0 larger, then that corresponds to a rescaling my trace. So the Euclidean thing knows the relationship between that S0 term and rescaling of the trace. The canonically quantized theory doesn't really know what S0 is, so it just knows that the trace can be rescaled. But essentially the two things are the same thing.
Okay, so the second point is, I wanted to actually ask you what you achieved with the GNS construction for the Euclidean path integral, because it seems like you just rewrote the states. And
sorry, say that again. Like, zero state.
Rewrote the
states. Yeah, but the point of that rewriting is, okay, A, it manifestly says why the canonical construction is always giving the same thing as the way we do Euclidean entropy computations, which was always, involve some hand wavy, hey, let's pretend there's a CFT and do stuff based on that. The other thing that it does is it makes it very manifest that the two algebras are each other's commutants. So that it genuinely, you could imagine that if you have some really long wormhole and I act with something in the middle, that there's some well-defined operator that commutes with everything on the boundary, that like does that thing in the middle. But roughly for reason, yeah, for the same reason that it doesn't happen in ADS CFT, or that we don't want it to, then it doesn't happen in this. But it's a bit of magic to make it.
So Geoff, I have two questions.
Yeah.
First, it seemed like you assumed there was an action of SL2 on the matter Hilbert space.
Yes.
Is that obvious for everything you write down?
I mean, it's like having an action of the Poincare group on GOT Hilbert space.
Oh, that's all.
It's the isometries of ADS2. So yeah.
The other thing I didn't understand, I saw why this is type 2. I assume you're thinking that of the hyperfinite type 2.
Yeah, I expect it should be
There's an
hyperfinite.
argument that it's a hyperfinite one rather than some more.
Yeah, it should be hyperfinite, I think. I don't have anything particular to say to that. Yes, so there is a unique hyperfinite type 2 to infinity algebra. That's sort of like the fact that there's a unique d-dimensional algebra for any finite d. The hyperfinite type 2 infinity is the only one that will normally ever shows up in physics, except in very rare circumstances. Just because there's only one algebra doesn't mean there's not like interesting different algebras. That's just like a purely abstract structure, right? Like there's a lot of different finite dimensional algebras and different theories that we think of in different ways, but at a purely algebraic structure level, they're just defined by their dimension and the size of their center, basically. So yeah, the interesting part is how it's related to matter boundary operators and the Hamiltonian and so on.
It seems that for super GT, the algebra is type 2-1 instead of type 2. What's the...
Yeah. Sorry. So it is type 2 infinity. It's the same way, but in super JT, there exist like discrete eigenstates, the Hamiltonian with exactly 0 energy. If you project the Hilbert space, you can project the Hilbert space into HR being equal to 0 or HL being equal to 0 or both. After you project either algebra into its appropriate Hamiltonian being 0, then you get a type 2-1 out.
Similar question. So do you have a formula for H left and H right in super JT?
Yes.
Analogous to the formula?
I can show that to you. I didn't have time to put it in there. I can send you some iPad notes. that are unreadable. But if you want the formula for your stuff, I can totally send it to you. It's complicated, but it's sort of the obvious thing.
Another related comment is, I think if you take the double scaled stuff, and you define an algebra in terms of these random operators, right? So you have a string of random operators, and then you literally take the triple scaling limit, I think you probably land on this construction on the nose.
Yeah, I expect that's probably true. Yeah. So that's what we're saying. I think the one thing is that you have a special matter Hilbert space, right? Because it's sort of free particles. But that I think if you wrote down the one particle thing and it looked pretty similar. If you like took a some Fock space thing, I expect you'd like get this.
Just a quick question. What do you mean by the Schwarzschild corrections? Could you say one?
I mean, if I go to very low temperatures, then the density of states it's like it's a cinch of square root, sine of square root e rather than e to the square root e. Yeah, I mean that. Yeah, Matt.
Okay, yeah, I mean, so the connection to Hawking radiation, I mean, is it, Hawking's original calculation of the Bekenstein-Hawking entropy used the Hawking temperature in the first law to get the rate. So are you basically confirming that calculation in the system, and you're saying, well, if there's no Hawking radiation, then of course Hawking couldn't have done that calculation that way, and so it's garbage,
Yeah, so in the paper we put out in September, where we were really taking a semi-classical limit, then there was a very close relationship between the fact that smooth states look thermal in Rindler modes with a Hawking temperature and getting the type 2 algebra having a trace that looks like e to the a over 4g that makes everything work. In this theory, it's like less obvious, that relationship, because you don't have a precise causal wedge, and so you don't have a precise bulk algebra, but it still matches the Euclidean answer, and adding matter still seems to be the key thing that makes the algebra a factor rather than having a center. And so I don't have a precise way to say they're related here. They're related in the semi-classical limit of black holes in a precise way. Yeah, I should say, Hawking's derivation is the first law, and therefore getting A over 4G is a great derivation, but it is a derivation of a classical thermodynamic entropy. It's not a derivation of a statistical entropy. I think there's a clear difference between the two. We then conclude probably it's also a statistical entropy because we know the history of the late 19th century and Boltzmann and how classical thermodynamics evolved into statistical mechanics. But just from Hawking's calculation, all you're learning is about classical thermodynamics.
There is a statistical mechanics behind it, you would arrive at the same conclusion.
Yeah, but this is deriving that statistical mechanics in a precise way. It's the statistical mechanics of this out.
Instance of that. I mean,
I would say this is in the classical black hole case, this is like a very souped up version of that, where we're throwing a load of maths at the problem and getting it to admit that the only way that classical thermodynamics can come from is statistical mechanics, which is like a non-obvious claim, even if we sort of all expect it. In JT, it's like, small.
This is perhaps baseless speculation, but do you expect with the issues here, like this Euclidean to Lorentzian interpretation, to extend to higher dimensions? And if so, why? If not, why not?
Yeah, to the extent that things are well defined. Don Morolf has been thinking about that in the last week or so, and wanting to say So I had I maybe should have let Edward answer that question, because I had a conversation with Don, because he got very excited and wasn't sure how much we were already saying, and I don't want what we're saying to be influenced by my conversation with him. We were basically just talking about JT gravity, but I think obviously we'd want to say this is more general, at least in spirit, to the extent that bulk path integrals are well defined.
Let me ask a question. So if we have a very long wormhole with a lot of entropy in the interior, but very low energy, then the entropy would be very low, like the entropy of the low energy.
So in JT grabs you with matter without having wormholes, then you can't ever have that, because S0 is infinity. So no matter how much bulk matter you put in, you can never make a bag of gold, because no matter how large the amount of matter. So if you put in, if you put in a load of matter, keeping the energy fixed, I think in general it will make the entropy smaller. Certainly in the super JT case, then you wanted to say that it makes it smaller, and indeed, in our calculations, the empty wormhole is the maximally entangled state, and so it definitely does make it smaller because it sure as hell can't make it bigger. I would expect the same thing is true in. I think generally making anything that's not the Harder-Hawking state will make the entanglement entropy smaller at a given energy, right? So the empty ADS Harder-Hawking state gives you thermal states, so they have maximum entropy condition on some energy.
One difference with higher dimensions is that the answer you gave Roni doesn't work in higher dimensions, right? You said, oh, there's an ambiguity in rescaling the trace, and there's this parameter S naught, but that's not true.
Why I said modulo bulk path integrals being well defined. I think the words Dom was wanting to say is, let's just assume that there's some string field theory or something in the bulk that cures all the divergences and makes it well defined. And then we can just start defining algebras in this way by this sort of formalism of strings and gluing traces together and stuff. Yeah.
Well, here is all work. In high dimensions, it's very much not.
Further questions?
A small comment, but like if you just take a really long wormhole, you can entangle the states of the whatever matters in there with some, and then make the interior of the long wormhole an island. But then
no, you can't. Yeah,
you can't do that because that would involve wormholes, and we've infinitely suppressed wormholes. So S naught is infinity, so you can never. That is the answer I gave one. That was not the question he was asking, but I refer to that answer.
But he will not survive as something.
I think it hopefully, I'd like to say that it should survive finite S naught. I don't think finite S naught JT gravity with matter is well defined without adding more stuff in. So I think that's what goes wrong there, is the theory stops being well defined. I think the theory is well defined with infinite S naught, and in that case, there's no islands to become.
If there are no further questions, let's thank